the electronic device is very small. It can be portable, and it is fairly cheap. So in many cases, it is preferred as a biosensing devices. And as we can see here, if we put add in sufficiently negative potential, we can reduce these metal ions. For example, for lead, it's at about minus 0.5 volts. Cadmium, minus 0.75 volts, and zinc, it's about minus 1.1 volts. So from electrochemistry, it also produces distinctly different peaks, just like fluorescence, and we can also regard it as a multicolored detection for DNA molecules. Okay, then I will show you some examples that we use Q dots to develop protein chips. I guess many of you have heard of protein chips. It can be used for simultaneous detection of many, for example, cancer biomarkers, so that with one droplet, it is possible to know what kind of cancer one patient had. The basic idea of protein chips is actually very simple. One just print antibodies, different antibodies at the surface of a glass chip. This glass chip has some functional groups so that proteins, antibodies can bind, conjugate at the surface. And at each point, it's just like a printer. So at each dot, it contains many antibody molecules which can capture antigens from the blood. And then we add detection probes, which is also an antibody that bind to the other side, binding side of the antigen. As I said, as I mentioned yesterday, it's like a sandwich, and this detection probe is tagged with fluorescent molecules, so that we can use either a microscope or a scanner to read out the signal, and the intensity shows the concentration of the tumor biomarkers in blood. And there are various ways to improve the performance of protein chips. For example, we can use both microfluidics and Q dots to ease the fabrication process with microfluidics, and to improve the sensitivity by Q dots. We did it this way. This is a small protein chip device, which you may, if you have interest, you can find it in my laboratory. Basically, we use a plastic called PDMS, which contains many microscale channels. And we adhere this PDMS at the surface of glass. Then we flow antibodies through this channel. And antibodies will be conjugated to the surface of the glass and leave behind a line of antibodies. Then we peel this PDMS off and put another PDMS with the channel just crossing this the original line. So in this way, we flow the blood samples through these channels. If there are any protein tumor biomarkers inside the sample, it will react with the antibody line just as a cross section. So we can see that the results are just like this. At a cross section, at this rectangular, this is a signal. If there's fluorescence, this means in the blood there are some specific cancer biomarkers, and the intensity shows the concentration of these biomarkers. And in our design, we use Q dots rather than organic dyes. This Q dot is conjugated to the detection antibody, and it is brought to the proximity of the glass chip with this sandwich structure. And we can see the advantage of using Q dots rather than organic dyes. This size 3 is a common organic dye, and this Q dots, we can clearly see that at about 250 picomolar, with size 3 we cannot see any signal. But if it's Q dots, we can even see the signal at about 250 femtomolar. So the sensitivity has been improved by at least 4 orders of magnitude by using Q dots because of its high fluorescent intensity. And for protein chips, it is very important that it can be used for real blood tests. And we can see that this picture basically shows that our protein chip works equally well in pure buffer solutions and in serum, which contains many high concentration non-specific proteins. So the selectivity and the specificity of our protein chip is very good. And it is also possible to do multiplexing with different colored Q dots. For example, this red dot is specific for the CEA, which is a cancer biomarker, and this green Q dot is for AFP. This is specific for liver cancers. So we can simultaneously detect both cancer biomarkers in one chip. Okay, I talked all the time about cadmium-based Q dots, but while I have said that we can coat cadmium-based Q dots so that it has been fairly biocompatible, but it is still cadmium, so eventually cadmium may be released if it is used in bodies. So here now, cadmium-based Q dots have not been approved by FDA as an imaging reagent for human beings. So that's why people are interested in many other in Q dots with other materials, for example, with silicon. However, silicon dots till last year, the quantum yield of silicon dots is very, very low, just below 3%. So that's why silicon dots are not used, and still cadmium-based Q dots are widely used. Last year, we and our collaborator in City University of Hong Kong, Professor S.T. Lee, both of us collaboratively developed a new way to encapsulate many silicon dots in a nanosphere by using PA, polyacrylic acid. Through this way, we can obtain fairly monodispersed nanospheres with a size of approximately 50 nanometers or 100 nanometers or 200 nanometers. We can control the sizes. And most importantly, silicon dots inside the nanosphere retains their crystalline structure as shown by this high resolution TEM. Very interestingly, for silicon dots, the fluorescence is very poor, very broad, and the intensity is very low. But after we encapsulate silicon dots into a nanosphere, the intensity increased dramatically, and the width, halfway width has been very sharp, fairly sharp. And it is fairly stable after 180 days, almost no signal fluorescence decrease. So this means that it's highly stable nanosphere. And the quantum yield has been increased to about 17%. It's still not as good as cadmium-based quantum dots, but it has been high enough to be used in biology. So we use this silicon nanosphere to label cells, and we can clearly see that cells are labeled with red-colored Q dots. And this picture just shows that after irradiation with UV light for many a few hundred seconds, our Q dots are still shows beautiful fluorescence. But if it's FITC dye, just after 45 minutes, after 45 seconds it decays, and after about 90 seconds, almost no fluorescence. And this Q dots, this silicon nanosphere is even more stable to the photobleaching than the cadmium-based Q dots. We irradiated with a high-power UV lamp. In this condition, even cadmium-based Q dots, we can see fluorescence decrease at about 20 minutes. But our nanosphere, after about 60 minutes, only 20% decrease in fluorescence. This nanosphere is very good. However, it still has a disadvantage. It's not pH stable. So this limits its biological application. Because we have, in many situations, we have to conjugate antibodies to nanospheres. And this conjugation process usually has to involve low pH or high pH solutions. More recently, we find that if we partially oxidize silicon nanospheres, we can reduce the size of these nanospheres. And more importantly, after this partial oxidation, the photoluminescence, the fluorescence of this nanosphere becomes even better. With the peak is even sharper, and the intensity is even higher than the original nanosphere, and the stability is a little bit better. And more importantly, the pH stability has been significantly improved with this partial oxidation. This line shows, this curve shows the pH stability of original quantum sphere. We can see that it is stable in the acidic solutions, but after pH 6 or 7, the fluorescence almost goes to 0. But with this partially oxidized nanosphere, even at pH 14, the fluorescence is still about is over 80%. So this means that this is very pH stable. Then we can do very easily do bioconvex conjugation. This TA-coated quantum nanosphere has carboxylic group at the surface. So we can, based on the, if we add antibody with amine groups and with the EDC and NHS, we can conjugate it to the surface of Q dots. And this bioconjugate is very stable. After 1 month, and the fluorescence almost does not change. So with this bulk conjugates, we can do immunoscaling. This picture just shows that the cellular skeleton of the cell has been stained with our nanosphere, while the nuclei was stained with just an organic dye. Okay, then I will stop this quantum dots part by this beautiful picture. I summarize here the Q dots can be used for multicolor microarrays like protein chips, and it can be very useful for immunochemistry like in fish, fluorescent in situ hybridization. It can be very useful for biosensor design, and for ex vivo cellular imaging. It can be also very useful for in vivo animal targeting in some cases. So if you have interest, you may read this excellent review in Science in 2005, and you will find more detailed information about Q dots. Okay, then go to nanoparticles.
Maybe this would be a good place to
okay.
make.
Yeah, good.
So, are there questions to this part of the lecture? Questions? Well, it's not to resume in 10 to 15 minutes.
Yeah.
那个